So what is, again, the definition of a ring? A ring R is, well, first of all, a non-empty set on which there are two binary operations, traditionally and in the theory called addition and multiplication. So we can go ahead and write a plus sign and a multiplication dot. Though you should keep in mind that there are some weird examples of rings. And in fact, in general, in the abstract, ring theory can get pretty weird, especially when you consider finite rings. It's a strange thing. In group theory, we focus on finite groups. I mean, we could do the same kind of thing in ring theory. There are finite rings and there are nice finite rings. But in general, if you focus on finite rings, things kind of get so weird that it just is super difficult. So we focus more generally in ring theory on infinite rings, actually. And in particular, our main emphasis is going to be rings of polynomials, though we need to think about these other examples too to help build toward that. So we have two binary operations, addition and multiplication. That is the main kinds of operations that are relevant for most examples, not the really weird examples. Satisfying what? Well, again, the fact that we're calling them binary operations for our author, at least, means that they're closed. That implies closure. Not every author says that the word binary operation implies closure, and they add the word closure in there for extra emphasis and define what it means. But for us, this implies closure. But that's always worth emphasizing, I think. It's closed under addition, it's closed under multiplication. But what else? It's always a group under addition. And in fact, you can say a little bit more. What else can you say under addition? It's an abelian group under addition. So addition is commutative. That is part of the assumption of rings. Could you get away with assuming it's not necessarily commutative? I suppose. But that's not what's done in ring theory. So, in fact, the book says that commutativity under addition is labeled as the first property. The other properties under addition are the ordinary group properties, but written with additive notation. It's associative, so this is true for all A, B, and C in the ring. There's an identity. The identity in the abstract is called zero, additive identity. And in many examples is a zero, the number zero, or maybe the zero matrix, or the zero polynomial. Technically, the zero polynomial is not the number zero, but it acts so much like the number zero that it doesn't really hurt to pretend it's the number zero, most typically. But, you know, polynomials. Here's another weird thing. Are we going to think of polynomials as functions or just polynomials? And what's the difference? There actually is a difference. If you think of polynomials as just polynomials, just expressions, essentially they're just symbols that, well, we can add and multiply according to certain rules. They don't have much meaning beyond that. Like, what do the powers mean necessarily? They could be just placeholders in a sense. But yes, we also can think of them as functions. And that's what we usually do, right, in math, is we think of polynomials as functions. And ultimately, we will plug numbers into them, and we could graph them. But as a pure algebraic object, you don't have to think of them as anything but just symbolic things that don't have any necessarily much meaning. Anyway, coming back to the definition here, there is a zero. There exists an additive identity labeled zero. such that a plus 0 equals a for all a in R. Do I also need to write that 0 plus a equals a for all a in R? Don't have to write it, right? Because I'm already assuming it's commutative under addition. It's an abelian group under addition. So if I write a plus 0 equals a for all a in R, it also means 0 plus a equals a for all a in R. And existence of inverses. For all a in R, there exists an additive inverse labeled negative a, or the opposite of a if you prefer. Probably the best terminology is additive inverse. But yes, labeled with a negative sign, such that a plus negative a equals 0. And yes, again, by commutativity of addition, that would also imply that negative a plus a equals 0 as well. Now, we have this binary operation of multiplication. And again, calling it a binary operation already means it's closed. What else do we assume about multiplication? We do assume the associative property. So I'm not using a dot in here, right? And that's, of course, traditional in math. If you're using letters to represent numbers or quantities that are being multiplied, yes, you could put a dot between them to emphasize the multiplication, but we don't usually bother unless the dot happens to be a dot product. Then it is a good idea to put a dot so there's no confusion. But here you use just juxtaposition. You put the letters next to each other and it's understood that you're multiplying. Of course, in computer programs like Mathematica, for example, you do need to put a star between letters or space technically to multiply them. Otherwise, it thinks of them as one symbol. AB would be one symbol representing one variable. This is true for all A, B, and C and R. And what's the final property? This is the last one listed. It's a completely new property that we haven't talked about before. Go ahead. Distributive property. And there you do need to write two kinds of distributive properties, technically speaking. A left distributive property, where you have the sum on the right and the element that's going to be distributed through the parentheses, so to speak, on the left. This is AB plus AC. And a right distributive property. I don't remember if the book changes the roles of the letters. Let me go ahead and look and see. Okay, they put the A on the right. A right distributive property. You do need both of those as part of the definition. Because again, the ring is not necessarily commutative under multiplication. So A times B plus C in parentheses could be different than B plus C in parentheses times A. If the ring, in fact, was a matrix ring, where all these letters represent matrices that are being added and multiplied in the usual way, although matrices, square matrices, I should say, matrix multiplication is not commutative. So you really would need both of these to be stated and proved if you're trying to verify it's a ring. So both of these are true, and you could call these 6 part 1 and 6 part 2 or something if you like. You don't have to do that for all elements in the ring. And again, this definition is very broad. There are lots of rings out there, and there are lots of rings that we're not even going to talk about in this class. And again, if you study finite rings, with this broad of a definition, things can get really weird. There are lots of weird finite rings that just, they're hard to think about, they're hard to classify. Weird things, unexpected things happen. We will look at Zn. I'll just jump to that example right away here. Zn, the ring of integers modulo n. If you call this the group of integers modulo n, or the ring of integers modulo n, as a set is the same thing, 0 through n minus 1. If you call it the group of integers modulo n, then you're only talking about addition mod n. If you call it the ring of integers modulo n, then you're talking about both addition mod n and multiplication mod n. This is, for any fixed positive value of n, a finite ring, if I'm focused on it as a ring. And it's relatively tame compared to how weird finite rings can get. Though it's weird as well if n is not prime. If n is prime, then it's not so weird. But if n is not prime, if it's composite, things will get a little weird. Okay, so we'll call this again the ring of integers modulo n. When I say that, I'm implying the two binary operations are addition mod n and multiplication mod n. You could write that down if you like. We will get into today even how this is a little weird when n is not prime. Okay. What else could we add to this definition? That's not the official definition of a ring, but can make rings more specialized that we talked about. And we could add extra adjectives to the description of the rings that we're talking about, or completely new words, like one that starts with an F. Field, ring, field. What other properties, well, for example, would a field satisfy? The most basic is existence of a one, a unity. Yeah, and you do want fields to be commutative. If R is commutative under multiplication, commutative under multiplication, i.e. AB equals BA for all A and B in R, then we call R a commutative ring. We don't say a Boolean ring. Again, you could decide, hey, I'm just going to buck tradition and call this an abelian ring. It's just that, well, you'd be in the minority of ring theorists. Okay, if you went to a ring theorist conference and you call these things abelian rings, they're like, oh, come on. We don't call them abelian rings, we call them commutative rings. Abelian, that's for group theorists. Yes, they would know what you're talking about. And they'd say, hey, what are you, a group theorist? Calling it a abelian ring. Actually, group theorists and ring theorists don't really talk to each other much. Oh, that's an exaggeration. But historically, they kind of just developed in different circumstances. So the terminology was a little different. And the group theorists wanted to honor Abel. So they, abelian ring. And the ring theorists didn't care about Abel. No, just kidding. We call our commutative ring. All right. There are commutative rings, though, that don't have a one. We talked about an example last time. Don't have a unity. The ring of even integers, 2z, or 3z, or all the multiples of 3, nz, all the multiples of n, where n is a positive integer. If n is bigger than 1, it's a commutative ring without unity. There's no 1. No multiplicative identity. But if a ring does have a multiplicative identity, if there exists a 1 in R such that 1a equals a1, and there I am writing both products. equals A for all A and R, then we call one a unity, and we say R is a ring with unity. Are there rings with unity that are not commutative rings? Yeah. Matrix rings that include the identity matrix. The identity matrix, right? Ones along the main diagonal, zeros elsewhere, would be the unity of a matrix ring. For example, the ring of 2 by 2 matrices with integer entries, or with real entries, or rational entries, or complex entries. I mean, those are different rings that I'm mentioning now, but those will all be rings of matrices that include the identity matrix in them. And they would be rings with unity that are not commutative. If it's both commutative and has unity, we say it's a commutative ring with unity. Add both words in. You do have to be careful though. And here, okay, maybe this will be the only example of a really weird ring that we look at. There's an example. Okay. Take a look at example 9 in chapter 12. Z6, focus on Z6 first. Z6, right? 0 through 5 under addition mod 6 and multiplication mod 6 is a ring. It's got a unity. It's commutative. Multiplication is commutative mod 6. But it's a little weird ring. For example, 3 times 4 is 0. Remember, the 0 is kind of a problematic element. I mean, it's there. We can't deny its existence. But it's problematic for multiplication because 0 times anything is 0. And if you make the multiplication table, it's not a Cayley table. It's not a group operation table, because, for one thing, because 0 is just problematic. So maybe we think about taking out 0 when we make the multiplication table. And maybe the multiplication becomes a group under multiplication. Maybe the multiplication table makes the ring a group under multiplication when you take 0 out. Maybe it doesn't. With n equal to 6, Z6, it doesn't. For example, 3 times 4 is 12, mod 6 is 0. 3 times 4 is 0 in this ring. That should seem bad. You multiply 2 non-zero elements and you get 0. That never happens in any other math class. Well, it's happening here. And yeah, it's quote unquote bad, but it is happening in rings, which is kind of like why we like fields better. It doesn't happen in fields. 3 and 4 in Z6 are example of what are called zero divisors. They are non-zero elements that yet multiply together to give you 0. Weird. Kind of makes your stomach churn a little bit. Why does that happen? Z6 does have a unity, the number 1, right? Now, the start of this example says that the set containing 0, 2, and 4 is a subring of Z6. We had subgroups before, now we have subrings. Will we have normal subrings eventually? Kinda, but we don't call them normal subrings. We use an even more beautiful word. We call them ideals. There are subrings of rings, and you could create new terminology, and there will be no quote unquote normal subrings, but they don't call them normal subrings, they call them ideals, and ring theorists are very proud of that. Which is so ideal. So this is a subring. What does that mean? It means it's a ring under the same operations as Z6, though it doesn't have a unity, or seemingly doesn't have a unity. I should say it seemingly, actually, because there's no 1 in it, right? 1 is the unity of Z6. But guess what? This does have a unity. 4. What? 4 is the unity. Why? Well, 0 times 4 is 0, mod 6. 2 times 4 is 2 mod 6, right? 2 times 4 is 8, mod 6 is 2. 2 times 4 is 2 mod 6. 4 times 4, 16, is 4 mod 6. 4 is acting like the unity. It is the unity of this ring. But it's not 1. And it's, wait a minute, it says 1 is the unity of Z6, and what? Are there 2 unities in Z6? Is 4 a unity of Z6? 4 is not a unity of Z6, it's a unity of the subring. 4 times 3 doesn't equal 3, equals 0. It's like a partial unity. Oh, weird. Yeah, finite ring theory. This is maybe the only example of that's really, really weird because of this fact that 4 is the unity of the subring, but it's not the unity of the original ring. Maybe this will be the weirdest example that we look at. Just a hint of how weird finite ring theory can be. There's a subgroup test. Oh, there's a subring test. How about that? Okay, what is a subring again? I said it, but here's the official definition. A subset S of a ring R is a subring of R if S is itself a ring with the same operations from R. The same addition, the same multiplication that they have in R. Don't define a new addition or a new multiplication. That would be a different ring that's not a subring. And it would still be a subset of R, but it would be not a subring because it's different operations. We are talking about the same operations here, still addition and multiplication mod 6 in this example. And just like there's a subgroup test, there's a subring test. A non-empty subset S of a ring R is a subring if S is closed under subtraction and multiplication. So the subtraction corresponds to the same thing as the subgroup test. A and B are in A minus B needs to be in S. That's analogous to A, B inverse being in H when H was a subgroup. We're using additive notation now. That corresponds to A plus negative B, or well, why don't we just write A minus B? Yeah, we are going to write subtraction symbols to mean this. A minus B means A plus negative B. But if subtraction is really addition, why isn't subtraction commutative? We think about that. Right? Addition is commutative. And here, this is essentially defining subtraction by addition. If subtraction is really addition, why is it not commutative? Trick question. Well, it's because B minus A really means something different. It means B plus negative A, not A plus negative B. That's why. It's important for future teachers, right? Maybe you teach your 4th graders, 5th graders, 6th graders about the commutative property of addition. And then you say, hey, I guess you probably don't learn about, you don't be real formal with properties until at least 6th grade, probably, maybe 7th grade. Then you say, hey, subtraction is really addition. And maybe you'll have some bright 6th grader who says, but why is it commutative? Okay, there's why. 5 minus 2 means something different than 2 minus 5. If you can get away with proving properties without assuming them, then you should not make it part of the definition. This theorem includes a bunch of properties on this page and the next page. I'm not going to show you the next page, which you could say, well, shouldn't that be part of the definition? And the answer is no, because you can prove them from the definition. A times 0 equals 0 times A equals 0, no matter what A is from R. Oh, could we prove that from scratch? Let's see. I always get a little nervous about these kinds of proofs because it's like there's always some trick. So this is a basic property to prove. Just like I told you guys how, like in Province stats, this is for a ring R. How like technically you might say the easiest part of the course is supposed to be the beginning, chapter 1 and 2, with like combinations and permutations. But I know with the problem solving with those, that I always feel a little nervous. Like, am I gonna do it right? Am I gonna think about it right? Kind of feel nervous with these kinds of proofs too. It's like, this is a real basic property. It should be really easy to prove, but it always involves some sort of little trick. And so it always just feels nerve-wracking. Let's see if I can do it from scratch here without looking in the book. So we got a ring R. Definitely has a 0 because that's part of the definition. Let A be an R. I want to show this is true. So what's the trick? I'm trying to show, for example, A times 0 is the additive identity. Okay, there are different ways to do this. Let's see. Maybe I should try to add A times 0 to something. And so if I get that something when I add, should I add to B? Maybe I should try adding it to 0, maybe. Okay. This is a proof attempt, maybe I should say. I'm going to go ahead and write down my idea, but it's maybe it's not a good idea. So maybe it's not really the true proof yet. A plus 0, A times 0 plus 0. What is it equal? You want to say it equals 0. That's the goal. Does it? It's a ring without not necessarily to have unity. I'm wanting to maybe use the distributive property here, but what do I factor out? Can I factor out a 0? But if I do, what goes here in place of question mark? If I put a 1 there, then I'm implicitly assuming the ring has a unity, and that's not part of the assumption here. Should I put A there? Well, that seems problematic too, because then I'd really sort of implicitly be assuming A times 0 is 0. I'd be assuming this 0 could be represented as A times 0. Okay, yeah, I guess that seems maybe like a bad thing to try. Let me try something else. Let me try adding A times 0 to A. Maybe this is problematic too. Maybe I need to look in the book. Because again, then maybe you'd want to use the distributive property. But again, it's problematic. What goes in place of question mark? Can't put a 1 because you don't know that it has a 1. Let's go back to my original idea. So my original idea was like thinking that I want to show this as 0 by maybe factoring out the 0. Maybe it would be doable from that. I think that's not what we want to do. I think we want to use the fact that 0 is already known to be an additive identity. Yeah, that's got to be the proper thing to use, because otherwise, why are you even bothering to write it? I mean, 0 is special, right? A times 0 plus 0 has got to equal A times 0. Since 0 is the additive identity. That's got to be relevant. And what's my goal? My goal is to show a times 0 is 0. Here's the trick now. Replace this 0 with 0 plus 0. Then use the distributive property. 0 does equal 0 plus 0, for sure. Then use the distributive property to distribute the a through. And then, yes, we can cancel the first a zeros. The cancellation law under addition does work, right? It is a group under addition. It's an abelian group under addition. We had the cancellation law from group theory. I sort of tried to emphasize canceling the a zeros on the left, but again, because it's abelian under addition, I wouldn't have to think of it that way. If this happened to be 0 plus a 0 up there, I could still cancel the a zeros, one of the a zeros. Tricky, 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 tricky. Oh, but it can be done. Okay. Am I going to put this on the exam? Well, probably not without help for this kind of thing. I mean, we have done it now. You could study it. I could say to study it, practice it. But would I put this particular one? Well, or maybe I'd put one of the other ones. You don't want to practice them. Okay. So I would either tell you that ahead of time, or maybe I'd give you some hints on the test itself. There are other examples that we should look at. This example, a little strange. It's called, especially the name, it's called the Gaussian integers. But guess what? I is the imaginary unit for from the complex numbers. I squared does equal -1. Zi with the I in square brackets is the collection of all complex numbers of this form, a plus bi, where a and b are integers. This is a ring. In fact, it's a commutative ring with unity. The unity is 1 plus 0i, and it is a subring of the complex numbers C. You can visualize it, if you like, as an infinite array. So Zi, the set of all numbers of the form a plus bi, where a and b are integers, is a subring of the ring of complex numbers. In fact, the complex numbers form a field. We haven't yet reminded you what a field means yet today. A field means it's an abelian group under addition, as all rings are. It is a ring, but the non-zero elements also form a group under multiplication. C star, where we take C and take out the number 0, is a group under multiplication. Every non-zero element does have a multiplicative inverse. But this is not a subfield of C, it's a subring. This is not a field. But it is a subring. We're understanding I squared is -1. It is, for example, closed under multiplication. 2 plus 3i times 4 plus 5i is something of this form. It can be simplified to that. 2 times 4 is 8. I'm foiling. 2 times 5i is 10i. 3i times 4 is 12i. And 3i times 5i is 15i squared. Minus 15. And this simplifies by combining like terms to -7 plus 22i, which is in Zi. Yes, we call these the Gaussian integers in honor of Gauss, but they are complex numbers. Integers because these a and b's are integers. Okay, it is a commutative ring. It does have a unity. The unity is the number 1, which can be thought of as 1 plus 0i. Let's end class today by focusing on what's going to be the most important kind of ring for us, polynomial rings. And let's do Consider the same example from last Friday. Z2x. What is this? This is the collection of all polynomials with coefficients from Z2. This is standard notation. Z2 with an X inside square brackets, kind of like Mathematica, square brackets, represents standard notation, all the polynomials you can make that have coefficients that are either 0 or 1. Haven't said what the operation is yet. I'll write this in words. All polynomials with coefficients that are either 0 or 1. Could you write that symbolically? Yeah. You could write it's the set of all expressions of the form an x to the n plus an minus 1 x to the n minus 1 plus etc. down to plus a2x squared plus, supposed to be a plus sign, plus a1x plus a0, where these a's, each ai is from Z2. For all I from 0 up to n. The operations are, how would you best describe this? It's best described as regular polynomial addition and multiplication, where you simplify the coefficients mod 2, not the powers, coefficients. The operations are quote unquote regular polynomial addition and multiplication where it's probably best to describe it this way, where the coefficients say are simplified mod 2, or for shorthand, say are modded by 2. Okay, I'm not sure that modded is a word, but I'm using it. Modded by 2. Is this a finite ring or an infinite ring? Z2 is finite. But the ring itself is infinite, because the degree of the polynomial can be arbitrarily high. N could be a million, a billion, a Google, whatever. Any positive integer for n. So this is an infinite ring. Infinite ring in spite of the fact that each coefficient is either a 0 or 1. Either a 0 or 1. It's a fairly interesting ring. And what are we after in the end with this kind of ring? In studying this kind of ring? We're after trying to understand factorization. Our goal, that's really a goal that's going to take us to the end of the semester. We have to work up toward it, is to understand factorization in this ring. And not just this ring, but other rings, rings of polynomials. Understand polynomial in this, understand factorization in this polynomial ring and other polynomial rings. I talked briefly, I showed you an example of a multiplication in this ring last time. Let's do another multiplication. X squared plus 1 times itself, for example. You do FOIL in the ordinary way here, x squared times x squared, it gets done first, giving you x to the fourth. Outside times outside is x squared times 1. Inside times inside is 1 times x squared. Last times last is 1 times 1. It's okay if you write this, x to the fourth plus 2x squared plus 1. That's okay, but don't stop there. Simplify. Mod the coefficients by 2. That one becomes a 0. So the x squared term goes away. And you're left with x to the fourth plus 1. And another way to look at this, so that's expanding this product, but another way to look at this equation is it means we can factor x to the fourth plus 1 as x squared plus 1 times itself in this ring. You can't do that if we weren't modding the coefficients by 2, right? If I didn't mod that coefficient by 2 to get 0, I could not say x squared plus 1 times itself is x to the fourth plus 1. And I could not factor x to the fourth plus 1 as the product of these two. Now you might wonder, why do we care? And that answer will be revealed as well. Factorization in this polynomial ring, as well as other polynomial rings that have coefficients coming from Zn, like Z3x and Z4x and Z5x, etc., is going to be helpful in the end for learning about factorization that you're used to, where you're not modding the coefficients. Especially in chapter 17, that's going to be a big highlight for us, is that learning how to do factorization in this polynomial ring and other similar polynomial rings is going to tell us good information about factoring in situations that you're used to. Factoring in general, when you teach factoring to kids, it's a pretty hard skill, factoring polynomials. A pretty hard skill for people. And, well, you're going to learn more about it. That'll be our main application of the subject. I'll just end by saying, coming back to a non-polynomial ring, that Zn is a field if n is prime and not a field if n is composite. And even more than just saying it's not a field, it's not a very nice ring, so to speak. When n is composite, it has 0 divisors. Zn has quote unquote 0 divisors if n is composite. Like 3 times 4 equals 0 mod 6, for example. There are rings that are not fields, but also have no 0 divisors. The most prominent example is Z itself. Z is a ring that is not a field, but it's a nice ring. It also has no 0 divisors. So in that sense, it's a fairly nice ring, even though it's not a field. This kind of in-between ring in terms of niceness is called an integral domain. Integral related to the word integer, because this is kind of the prototype. It is a so-called integral domain. Lots of new terminology in this subject. Rings, fields, integral domains, unities, units. Okay. One thing I didn't mention today was what it means for one ring element to divide another. That's related to factorization. X squared plus 1 divides x to the fourth plus 1 in that ring, for example. You can make sure you read about that. Okay. Have a good day.